In this video, we are going to continue to discuss the compression and stretching of a function on the horizontal direction. Previously, in the previous video, we was talking about how to stretch and compress a function horizontally. So now we are going to discuss how the function is to be compressed and stretched vertically. So this is vertical compression and stretching. The previous video was on stretching and compression vertically. Okay, before we continue to discuss how to compress, stretch the function horizontally, let us visit the mechanisms of compressing and stretching a function vertically. So when you stretch a function vertically, when you compress a function vertically, say from this function to a function like this, which is I think 3x. Sorry, you compress it vertically, then the function of square root of x become say 1/3. So when you do the compression, you have to be aware that we are compressing this horizontally at the fixed values of x. So every values of y on the original functions is to be compressed to a new values of y1, where the values of y and y1 are to be compared at the same values of x. So that the values of y1 over y is a factor of 1/3. Okay, so y is always larger than y1 by a factor of 3, and y1 is always closer to the x-axis. That is what we meant by compressing the function vertically. So the compression is done along the constant x. Now, if you were to compress a function horizontally, say you have a function y equals to square root of x. In order to compress the function horizontally, what you mean is that you have to compress the function at the constant values of y. So say this is a constant values of y. You would like to take every values on this point, which is say like on x1, to a point which is say closer to the y-axis at a values of x2. Okay, so that is what you mean by compressing the functions horizontally. By here we say a factor of 3. So in that case, the distance of x1 from x2 is equals to 3, such that the distance of x2 is closer than the distance of x1 from the horizontal axis of y. Okay, so the relationship between the x1 and x2 coordinate is fixed by the compression factor, and you do that along the common values of y. So every single values on y is to be compressed closer to the y-axis from this point to a new point. So you do that for every single values of y from here to somewhere here. Right, so you construct all the points from y to form a compressed function. So this is the compressed function. Let me call this y3, where such that the values of the compressed function at y3 and y1 are fulfilling the condition that the values of the function y on, say, x1. So maybe I should refer to these 2 points more concretely. So let me look at the x1 here and x2 here. So this is the point of x2 and this is the values of y . This is the values of y3 evaluated at the point of x2. Right. So this is a common values of y, and this point is the values of the function y at x1. So this value at x1 on the curve of y and these values of the function y3 at x2 are the same, because they are to be compressed, because the function y is to be compressed horizontally. So that is the mathematical relationship we could write down to relate 2 points on curve y and y3. And we also know that the relationship between the original coordinate of x and the compressed coordinate of x are related by the compression factor. So more generally, this is the k. So you can express x2 to be x1 by k, or you can express x1 equals to k times x2. So I'm going to rewrite these equations to be y of x1, which is k of x2, and this is y of 3, which is x2. Okay. Maybe this is not a good way. Maybe the better way is to write y of x1 is equals to y3 of x2, where x2 is x1 divided by k. Okay. So so this is x1, this is x1. So this statement is the same as replacing x1 symbol by x. So these 2 statements are exactly the same. Okay. So what I have concluded is that the relationship between y and y3 are such that y3 is related to y1 through this very simple relationship. In other words, if you have a function of y, you would carry out an operation of replacing x by dividing x with k. If you do that operation, the function of y will be brought to the compressed function of y3, where y3 is just obtained from y by replacing x with x over k. So the expression of y of x is square root of x, and you're going to replace x by x over k. So this will be just x over k. So I come to the conclusion that the function y3 is square root of x divided by the factor of k. So this should be then the formula for a function that is obtained by compressing the original function horizontally. So if this is my original function, y3 should be a horizontally compressed function that would be like this, and this is y3. So y3 is expected to be lying on the left hand side of y, and if you compare the values of x on y3 and the values of x on y, then you find out that this divided by this would be a ratio of 1/3. So to check that whether this is correct or not, I'm going to see if my function of y3 defined as this is indeed reproducing an vertically and horizontally compressed function. So let me go to my Mathematica. I'm going to define my y3 as the square root of x divided by k. So this is my Mathematica code. Originally, I have a function of square root of x. So now I'm going to define my function of y3, which I argue it has a form of square root of x divided by the compression factor of k. So that is what I expect it. So when I plot this function of y3, I expect the y3 to be lying on the left of the original function. So let's see if this is true. y3, I plot y and also y3 and see the y3 is lying on the right hand side of the function of y. It means my argument for obtaining the expression for y3 is wrong. So by dividing x with a k does not compress the function horizontally, but it actually stretch it horizontally instead of compressing it. So I must have done something wrong in my argument in deriving the compression formula for the function. So let's check where have I gone wrong. Okay, so the compression of the function is derived based on these statements. So let me see if my statement is correct. So when I compress it horizontally, the values of the function y at x1 should be equals to the values of the function y3 at x2. So that is a correct statement. And then if it's compressed, then the ratio of x2 over x1 should be such that x1 divided by x2 should be a factor of k. I think that is the more accurate statements. So I think that is x2, yeah, I think that should be correct. x1 is larger than x2 by a factor of 3. Okay, so if that is the correct statements, then my values of the function y at x1 equals to y3 at x2 is correct. Okay, so maybe I have done something wrong somewhere here. So maybe let me start over again from here. So the correct statements is the function of y at 1 is having the same values of the values of the compressed version y3 at x1 over k. Okay, so to derive the formula for y3x, what should I do? What I should do is that let me try to show you some simple algebraic tricks. So I look at this one. I said, okay, now I would call a symbol called q. I'll call q to be defined as x1 divided by k. So in the language of q, these statements is then expressed as y of x1. So x1 is equals to k times q. So here I'll replace x1 by k times q. Then the right hand side is y3 of q. Okay, so that is almost what I want. I think this is the more correct versions for the formula of an compressed of an horizontally compressed function. So next I want to do is that I want to revert back the symbol of q to x. So y3, I'll replace q again by x. Then the y of kq is then kx. So that is a relationship that relates the function of y3 to y. So I think that is a more correct version than the one that I have derived here. So this is a wrong workings. So please forget about it. So I'm going to look at this function. So according to these definitions, I come to the conclusion that if you have an original function y of x, and if you perform an operation of replacing k by k of x, then you will arrive at the horizontally compressed version of the function y3, where y3 is obtained from y by replacing the x in y by kx. So y function is square root of x. So if you replace x by kx, then what you get is an expression of kx. So here the function of y3 is just the function of y with x replaced by kx, which is just the square root of kx. So by right, this is the horizontally compressed version of the original function y. So I should define my function as the product of k times x instead of x minus k. Okay, so let me check again if my working is correct. If my working is correct, then this expression should reproduce a compressed version of the original function square root of x. So now it looks more appropriate. You can see that these functions, which is the y3, and this is a function of y. So if you draw a line horizontally, then if you fix the horizontal line for the same values of y, say 0.5, the values of x here is 3 times smaller than the values of x at this point on the function of y. So I have now confirmed that by multiplying the argument of y of x by the factor of k, you arrive at the horizontally compressed version formula for the function. So that is the conclusion I have to make, right? So you have an original function y equals to square root of x. Sorry, not this one. So here you have an original function of square root of x. When you multiply the argument of x by k, you arrive at the compressed versions of the graph, where the graph of the compressed version is lying on the left of the function y. To be more specific, the compressed versions is k times closer than the corresponding point of y on the y function. Okay, so here on the same values of y, the x values here is closer than the x values of here, right? So this is 1, this is 3. So that ratio of the x's on this point and this point are number of factor 3. Okay, so if you understand how we arrive at the compressions of a function horizontally by replacing the function of y by y3, where y3 is obtained by multiplying the x with k, then you should understand that in order to obtain the stretched version, the horizontally stretched version of the function is just the opposite. That is, the stretched versions of the horizontally stretched version, which is this line, this curve, is obtained from the original function, where the argument of x in the original function is to be divided by the stretch factor of k, right? So that is the formula for stretching and functions horizontally. So if this is correct, then we can see the effects of the stretch function by using Mathematica. So according to what I have explained earlier on, if you divide the x by the factor of k, where k is larger than 1, then y4 is the horizontally stretched version of the original function. So that function of y4 should be this one, which is the red color one, the red color function, which is lying on the right hand side of the original function. So I'm going to press my button and plot out the function of y4 and see whether if this is correct. Okay, so I have three functions. The original function y, the horizontally compressed function of y3 lying on the left of y, and the horizontally stretched functions of y4, which is lying on the right hand side of y3. So that finished up our discussions on the compressions and stretchings of a function along the horizontal direction. Okay, so this is just another example. So if you look at this function, original function is square root of x. So if you multiply x by a factor of 2, that g amounts to compression or stretching. Okay, so the answer is that amounts to, okay, you can figure it out yourself. Okay, so that is the discussions that I'm going to end here. I'm not going to continue, but you should try to understand how the compressions and stretchings of a function horizontally and vertically can be done. So the last part I want to talk about is a simple operation on the function. Here we are talking about reflections operations. So if you have an original function, say y equals to x, y equals to square root of x, you can reflect the functions about the y-axis. The reflection can be easily done by carrying out operations of replacing all the values of x by negative of x. When you carry out the operation of replacing x by negative x in an original function of y, then you would arrive at a new function, y1 for example, where y1 is the same as the function of y, where the y is replaced, where the argument of x in y is replaced by x. That will give you the reflected versions of the function about the y-axis. So in order to reflect the functions about the x-axis, what you have to do is just carry out operations of replacing values of y by negative y. Right? So let me write it in a more formal manner. If you have a function y, you carry out the operations to replace all values of y by y. Okay, maybe I should write this as y to be transformed into a new function. I call it y2, where y2 is obtained by replacing values of y by minus y. So under these operations, the y function will become y2, where y2 is just obtained by replacing y by minus y. Right? So this is the function of minus y, where the original y is square root of x. So this function of negative square root of x is just the reflected versions of the original function y equals to square root of x about the x-axis. So this is the reflections operations. So to conclude, let me write this down on a whiteboard. So if this is the original function, then to reflect the functions about the y-axis, so that when you reflect it, this graph will become a graph that looks like this. And this graph, which I label as y1, is obtained by replacing all the x by negative x. So that is obtained as 1 of minus x. Okay, so this graph of y1 is just the reflected versions of the original function about the y-axis. Now, in order to obtain the reflected versions of the function y about the x-axis, the reflections could be easily constructed. It will be just looking like this. Right? So every point of x will reflect it from y to become negative y. Right? So every point here about the same y, about the same x, you replace y by negative y. Replace the values of y by the corresponding values of negative y at the same values of x. So these new versions, well, these versions of the function, I call it y2, which is the reflected versions of y about the x-axis, is obtained by replacing all the values of y by negative y, which is this one, and this is the expression of square root of x. So y equals to square root of x is the reflected versions of the original function about the x-axis. Now, having discussing that, if I give you a function and ask you to reflect the functions about the y-axis, the operations to do is to replace x by minus x. So the function which is the reflected versions of this original function about the y-axis is just equals the original function of x, where you just replace the x by minus x. For example, just an example, say you have a function of, say, x cubed plus 1. So in order to reflect these functions about the y-axis, you just have to replace x by minus x, and you end up an reflected versions which is minus x raised to the power of 3 plus 1. Right? So if you plot this graph, you see that y1 is a reflected version of y. So maybe let me try to reproduce the graph of y3 here. I think the y3 would look something like this, if I'm not mistaken. Okay, so when you reflect it about the x-axis by replacing x with negative x, then what you will get, this is y, the y1 would be looking like this. Okay, y will be looking like this. So this is the reflected versions of y about the y-axis.